Right. Hello, guys. Welcome to our fourth lecture on the double integral theory. I'm sorry that this video is actually posted a day after March 6th. Today is March 7th because my laptop has some issue. But nonetheless, let us start the course. So I want to mention that in the textbook, there's two major topics in this application of double integral section. One is about probability, and one is about physics, where in the physics part, it's mostly major in the center of mass and inertia, some physical concept. Um, However, it actually takes a lot of time to introduce the probability part. So I think I will just omit that part and focus on the probability application. And I would also encourage you guys to just simply omit the suggested assignment about the center of mass or inertia. Just focus on the probability part. This section 15.4 will be on the quiz, but not on the midterm. So yeah, feel free to learn this lecture and have you guys can learn something about probability. Okay, so yeah, as I mentioned here in the preamble here, that we will introduce the application of double integrals with respect to the continuous random variable. And first of all, let me introduce the one-dimensional version, and then I will introduce the higher dimensional version of probability. So the first definition we'll be encountering is the one-dimensional continuous random variable. So basically, a random variable is a random assignment of numbers. So it is a number, but the number can be, it is basically like a function. And the input of a function is some random event, and that event will determine the output of the number. For example, we can say this x to be the height of the UMN students. Then the random event happens at when I'm drawing a person from the majority of the students, and I don't know which way I draw, right? So that's a random event, and the output will be the height. So that will be random variable. And we call the random variable x to be a continuous random variable if there is a continuous function f such that for every number a less than b, we always have this following formula. A probability of the number being within a and b can be given by this integral. F of x integrating from a to b. And in particular, this f will be called the density function of x. So there are several properties that this f must have. For example, f must be positive because you always have positive um, probability, right? Also, the integration of f on the whole real line should be 1 because the probability of x belongs to the real line is 1, right? So what I'm saying is that this guy must be 1, okay? Right, let's see some examples. So the first example here is the famous normal distribution. Let me go through some intuition. So suppose X, the random assignment, is, as I mentioned, the height of the student of UMN. So we're sampling student from UMN and we record the height of the sampling. So obviously, intuitively, you can assume that there is a small probability of that sample to be very high or very low, right? There is not much very tall person and very short person in the campus in general. And there should be a larger probability that X is moderate, like average height. So in that case, we consider this bell-shaped curve like this to model the sampling of the height of the students. And this is called the normal distribution. Normal in the sense that it is in some sense universal. We have a moderate high probability event, and for a tail, which is very high and very low, they both have low probabilities. So let me go through this function closely. We have 1 divided by square root of 2 pi. Pi is just the number you know, familiar with. And sigma squared is called the variance. We will be investigating this later. And exponential to the minus x minus mu squared divided by 2 sigma squared. The mu here is called the mean, which also we will develop later. But basically, this is what the curve looks like. So you'll see that I draw 4 different bell-shaped curve here. One is the red one, the yellow one, the blue line, and the purple line. So you see that the effect of mu here is the location of the bell-shaped curve. When mu is small, then the center of this bell-shaped curve will be small, so it goes to the left. And when mu is large, then the bell-shaped curve goes to the right. So in this case, both the yellow, blue, and purple curve have the same mean. Okay. And the variance here determines the spreading of the bell-shaped curve. So you see that the blue curve and the red curve shares the same sigma squared. So this is of the same variance. And when the variance goes large, then it spreads wider. So you see that the yellow curve spreads very wide, and the height, the peak, is very small. And when the variance is small, then you have a high concentration of the values. So the purple curve does not spread wide, and it has a very large peak at the mean. So basically, the mu, the mean, and the sigma squared, characterize two properties. The mean characterized by definition the concentration, basically the average of the distribution, so that the average of the height of the student in UM. And variance characterize how far away in general are you away from the center, from the mean. So if, say, you have very many outliers in UMN, there is some height people, there is some short people, there is also a lot of moderate height people, then in that case, the variance will be large because there is uniformly distributed height. However, if most people, I mean like a majority of people, have moderate height, then it will be centralized at the mean. In this case, it looks like the purple curve. Okay? So as I mentioned here, this curve represents the area below this curve represents probability of the height. So in this case, if we choose A and B, then this area will be the probability of this random sample having height between A and B. Okay. So this curve itself, the value does not have any meaning, but the area below that curve is the probability. So for example, the whole area under the curve should be what by definition. Okay, so maybe let us go through this a little bit more. So let us verify that this function is indeed a probability density function, meaning that the integral of this function should be U1. And we actually see this in the previous video on the polar coordinate. So let us do this again. If we try to integrate this guy from minus infinity towards infinity, then first of all, let us reduce this thing to our previous function. We replace this whole thing by u squared. So u will be x minus mu divided by square root 2 sigma. Whereas du is simply dx divided by square root 2 sigma. So don't forget mu and sigma are just constants. They can be 2, 3, minus 1, or something like that. So in this case, you have an extra Jacobian, the differential term, sigma 2 sigma, square root 2 sigma, and the integrand becomes exponential minus u squared. Whereas the integral upper bound and lower bound are still minus infinity to infinity because shifting and scaling does not actually change the upper and lower bound. And we see in particular this guy cancels out with this square root 2 and this sigma square in the square root. So we get 1 over pi, and this guy, we already computed this in the previous video. This is actually root pi, right? So we have 1 over root pi times root pi, and that is 1. So this shows that this guy is indeed a density function. If you want, I would say mostly it is covered here, but if you want more background on probability, you can see, I think, chapter 8 of the textbook, of Stewart's textbook. But I basically cover the part in chapter 8 and also the part in chapter 15 here. Okay, now with that definition, for a probability distribution, we can define the so-called mean or expected value. And usually we use the notation EX to represent the expected value. The E is emphasized here. And it is defined to be the integration over x times f of x dx. So you can sort of think of this guy as we multiply the value together with its probability. So in a discrete case, say we're rolling a dice, then what is the average value that you roll? So intuitively it should be 1 times 1 over 6 plus 2 times 2 over 6, and so on and so forth, right? So approximately, if you throw 1,000 times, then the average dice point that you're rolling should be 3.5. So this is similar. This is a similar idea. This is the outcome of the random variable. In this case, it can be the point of the dice or the height of the students. And this is the probability that that particular value is taken. So we multiply the value together with the probability of that value to be taken, and we sum it up or we integrate it up, then we can get an average value. So as I mentioned here, the mean represents the average of the distribution. So let us actually verify that this normal random variable, this normal distribution, actually has mean, mu. And this is actually some tedious algebra. So as I mentioned, the integration should be x times the density function, integrating from minus infinity towards infinity. So first of all, let us again change the variable to make life easier. So u to be this guy. So you have e to the minus u squared, and the change of variable, the differential again gives you du to be dx divided by root 2 sigma. So again, you have a cancellation here and here. Now the x here can be solved using this equation to be square root 2 sigma u plus mu. Okay, so be careful, this is u and this is mu. So let us split the integral into two integrand. One is this guy and one is this guy. So first of all, mu is a constant, so you can just factor that out. And again, here is root 2 sigma is a constant, so I factor that out. And we note that this guy is actually an odd function, right? This guy is even. This guy is odd. So the right-hand side have the area that is exactly the negative of the left-hand side. So this value goes to 0. Okay, if you're integrating a odd function within a symmetrical domain, then this will be 0. And this guy, again, we have already do this a lot of times. This is root pi, right? So you have 0 plus mu times 1 over root pi times root pi. So that is mu. So indeed, the parameter here, mu, is the expected value of the normal distribution. So we see that this diagram sort of makes more sense now, that this is indeed mu. Mu is the center of that bell-shaped curve. Okay, now let us define another notation, the variance. So the variance here is defined to be x minus ex, the expected value of the random variable, subtracting the mean taking square. So in terms of integration, it's simply x minus ex squared times f of x dx. So again, this is some random variable. We multiply the value by its probability, and then we sum it up. So the idea of variance, like we have to understand this intuitively first to know why we define it like this. The idea of variance is simply the way that we try to estimate how wide does the distribution spread with respect to the mean. So we want to see that how far away is x away from the mean, e to the x, ex, sorry. And I would say like sort of a more intuitive idea will be we evaluate this guy, right? The actual distance of x minus ex instead of squared. The reason we choose squared is because it is better to integrate and it is better to analyze. It is not, in general, not really convenient to analyze a absolute value function. So we would like to use the square version. And to accommodate the change of the unit, so for example, if we're doing height, then x has unit like feet or centimeter, right? But now you have centimeter squared or feet squared. So to accommodate that, we take the square root, and we define the standard division to be the square root of the variance. In this case, this s dx will be of the same unit as x. Okay, so now let us go back to the normal distribution cases. And we see that if x is normally distributed, then the variance of x is defined to be x minus mu. So we have already verified in the previous note that mu is in fact the mean of the normal distribution, right? So I want to show x minus mu squared times this guy can be evaluated to be the variance of x. So again, we perform the usual trick. We take u to be x minus mu divided by root 2 sigma, and we get the corresponding differential. And now the first term here is actually root 2 sigma u. So we see that we simply multiply this back here. And we have e to the minus u squared, which is the integrand here. Okay, so canceling all the constant, we get 2 sigma squared divided by root pi at the front, and we have u squared e minus u squared in the middle. So this is a very classical IBP. We take this, we split this guy into u times u to the e minus u squared. And we let this guy to be, actually u and v, but I use x and y here. So this is x, and this guy is dy. So integration of x dy is xy minus y dx. And in particular, dx is du, and you can do the indefinite integral of this guy. It's actually minus half e to the minus u squared. So we have xy, x times y minus y dx. And this guy actually goes to 0, because if it goes to infinity, then the decay of this guy overpower this guy. So it goes to 0. The same thing happens when u goes to minus infinity, then the decay of this exponential function dominates this polynomial term. So we are left with this guy. And again, we know that this thing is root pi, right? We have done this a million times. So you have 2 sigma squared over root pi times root pi divided by 2, and that gives us sigma squared. So indeed, as I mentioned here, the parameter sigma squared actually reflect the variance of the normal distribution. So when sigma is larger, that means that the average value of, the average distance of the distribution of value x is more away from the mean. So you have this highly spreaded diagram. And when sigma is small, that means all value is concentrated towards the mean. So it looks like this peaked distribution. Okay, so that's the definition for mean and variance. And we actually see that whenever we have a normal distribution of this type of density, then you have mean mu and variance sigma squared, meaning that basically you can read off the mean and the variance statistic from the density function here. The sigma is here and the mu is here. In which case, we often denote this distribution by x obeys the normal distribution with mean mu and sigma squared. Okay. Right. Now to another simple distribution and very common distribution, the exponential distribution. So this is usually used to simulate some stacking problem. So if the average waiting time of some query is 1 over lambda, then we can simulate this kind of waiting time to be exponential distribution. And the density function of this distribution is defined to be f of x to be lambda. Lambda is the same thing here, lambda e to the minus lambda x. And we only sample time from the positive axis. So that is basically because that you cannot have negative waiting time, right? So the exponential distribution does not take negative values. And this is a sort of diagram of how the exponential distribution works. We see that when lambda is small, that means that the average waiting time is large, right? So you see that the curve is very flat because it is possible that you have a long waiting time. The area here is large. And when lambda is large, that means that you have a small waiting time, right? So you have a highly peaked curve, meaning that you have a better possibility of getting a smaller waiting time, shorter waiting time. And obviously, when lambda is moderate, then you have something in between. You have a possibility of having a small waiting time or a long waiting time. Okay, so let me emphasize on this notation here. This means this is simply a function that takes 1 when x is larger or equal to 0, and 0 when x is negative. So basically, that means that when we're integrating f of x from minus infinity towards infinity, that we only care about the part which is in the positive axis. Okay. Right, now let us do some calculus work. So first of all, let us check that it is indeed a probability distribution by taking the integration over the whole real line and to see whether it is 1 or not. So as I mentioned, this f of x actually only contributes in the positive real line, and on that line, the density function is lambda e to the minus lambda x. So this is a very simple integration. You can do it by one-dimensional integral. The antiderivative of this guy is minus 1 over lambda e to the minus lambda x. When x goes to infinity, that goes to 0. When that goes to 0, this guy goes to 1 over lambda. So lambda times 1 over lambda is 1. Therefore, f is indeed a density function. Okay, the whole area here is always 1, whatever lambda is. Lambda represents a statistic that corresponds to the average waiting time. And that is what we're doing now. So that is actually verified that this model is a good model, meaning that the mean of this distribution actually reflects the waiting time. So let us compute the expected value. And that is, as I mentioned, defined to be x times the probability density f of x dx. And we say that this guy only contributes on the positive axis, right? So 0 towards infinity, x times lambda e minus lambda x. Again, it's a very classical IBP. We take u to be x, dv to be this whole guy, and then du is therefore dx, and v can be integrated up to be minus e to the minus lambda x. So we have u, v, minus v, du. Du is here, dx. And again, the first guy, when x goes to infinity, the decayness, the rapid decay of this exponential function actually dominates the growth of this polynomial function. And when x is 0, you simply get 0. So the first one does not contribute. And for the second guy, you again use the simple exponential antiderivative. You get minus 1 over lambda e to the minus lambda x. When x goes to infinity, this goes to nothing. And when x goes to 0, you simply get 1 over lambda. So you see that this is indeed what we expected, right? When you have an average mean of 1 over lambda with the time, then you should use this model. So for example, if you have a waiting line that has an average waiting time to be, say, 2 minutes, then you should apply this f of x with the parameter half. That will reflect your waiting distribution. Okay. And I encourage you guys to try to evaluate the variance. It is very simple. Simple 1D calculus, and you should get the 1 over lambda squared. Okay. So whenever you have a higher waiting time, a longer waiting time, then the variance will also be larger. So see that, for example, this case. This represents small lambda, so longer waiting time, right? And you can also see that it is spread widely in comparison to the blue and the yellow line, so the variance is also large. Okay, so now let us go to our central topic now. We have now sort of, I believe, familiar with the one-dimensional probability distribution, and now we're gonna head on to the two-dimensional probability distribution. And as I mentioned, this is not the central topic of our calculus. This is just a simple application of what you guys have learned about the double integration. So again, this will not be in the midterm, but the quiz. And I just want to go through these ideas and these topics to make sure that you guys know, okay, so this calculus thing is actually applicable somewhere. And actually it plays a central role in probability theory. So yeah, let us continue. So yeah, a 2D variable is essentially the same as a 1D variable, but now instead of a single number, we assign a random pair of numbers x and y, and it is continuous if there is a function f. In this case, f is defined on R2. There is a two-variable function, and that f should be satisfied by this equation. The probability of x is within a and b, and that y is within c and d can be evaluated using this double integral. The integration of f on the rectangle AB and CD. So this is just like a one-dimensional case, but you simply enlarge the domain to be two-dimensional. So we previously only have this guy. Now we have two variables, right? And in this case, the f here is called the joint density function of x and y because it is a joint random variable, right? You joint x and y together. So this is essentially different from the previous case in the sense that x and y might have correlation. In that case, the 2D random variable cannot be understood as a 1D random variable. You cannot split x and y up. So that is an interesting one because in most real life cases, the random variables has correlation. For instance, we cannot really identify the weight and the height to be an independent random variable, right? Because they must have some sort of correlation. I would say maybe in general, the higher person will have the larger weight, right? It should be in some sort of proportion. So in that case, you cannot treat them separately. can treat them together as a joint random variable, a two-dimensional random variable. So again, let us do some example because those are all abstract definition. So we say that a random pair x and y are uniformly distributed on some bounded set omega belongs to R2. So omega can be some rectangle, some circle, or some triangle. If the density is given by this guy. So let us break down these notations. 1 over omega, this guy is the area of omega. So for example, if we uniformly distributed over a square, 0, 1, and 0, 1, then this will simply be 1. And this is, again, a very tedious notation. It simply means that we take 1 when your point is within omega, and 0 when you are not within omega. So this function only values on the omega, and it takes the value 1 over omega area on the omega, and it does not take values outside the domain omega. Okay, so yeah, say for a very simple example, let's do a rectangular domain. Omega is 0, 2, 0, 2 times 0, 1. So in that case, f of xy would take half within this rectangle and 0 outside this rectangle. So obviously we can see that the area here is 2, right? So obviously the integral over f on this domain will be half times 2, so that's 1. So this is indeed a probability density function. Similar to the one-dimensional case, when you integrate on the real line, the one-dimensional distribution density function should give you 1. And now when you're integrating on the whole R2, the Cartesian plane, then a two-dimensional density function, a joint density function, should give you integration 1. Okay, so let us do a very simple example. What is the probability of the first coordinate to be less than x or equal to 1, and that the second coordinate is larger or equal to 3? So the first coordinate being less or equal to 1 basically means that x has to be within 0 and 1, right? And the second coordinate being larger or equal to 1/3, that simply means that y has to be within 1/3 and 1. And we know that this f of xy simply has value half within this domain. So you have half, and you integrate y from 1/3 to 1, x from 0 to 1, and that is 1/3. It basically means that this blue area is 1/3 of the area of the whole thing. Okay, so now how can we sort of connect the one-dimensional random variable and 2D random variable? There's actually a very nice connection. So we see that we can actually recover the distribution of the marginal random variable, x and y itself, by the joint distribution. So it contains more information in some sense. So let us see here. What is the probability of x within A and B? So in this case, we do not care about the random variable y, right? So the y can be everywhere. That is why this is R, the whole real line. And we care about x to be within A and B. So we're integrating this density function on AB cross R. So in terms of the graph, it is simply AB, and we're integrating on this strip. Okay. Right. So by Fubini's theorem, you can split the integration between y and x. So you get this whole thing, dy first, all the way from minus infinity towards infinity, and x goes from A to B. And let's look closely. So this guy is actually a function in terms of x, right? And this is actually a density of x by definition. Because we've seen previously that the definition for density is some function so that you have this equality satisfied. For every a and b, you can always find the probability of x within a and b by a function integrating from a to b. And this is indeed what we want, right? You see that in this case, this guy is the f of x that we want. So we see that by integrating over y on the whole real line, you will get back the density of x. And the same thing works vice versa. So let me go through this definition. Actually, it is more like a property in the definition. So we see that in a 2D continuous random variable with a density f, so f here is a two-dimensional function. You have two variables. And we see that the density, or usually sometimes called the marginal, of x and y can be computed respectively by f of x to be integrating of this density of y on the whole real line. And the same thing happens for y. We integrate f of xy on x for the whole real line. And in particular, we claim that, actually not claim, we define that when the density function f of xy is equal to their density functions, the marginals, multiplied, then we say that x and y are independent. Okay, this is the definition. And I would like to go through more about independency and why this is defined like this, but basically this sort of coincides with our intuition on independency. Basically, you can develop some concept called conditional probability, and we can actually show that when x and y, sorry, maybe this is a better phrase, when x conditional on y is equal to the distribution of x itself, then this thing will happen. And that is why we define the product case where f is equal to fx times fy to be independent. But for now, we don't really have to care about the meaning of that. I just simply give you the definition. And there's obviously some intuition behind that, which is what I just mentioned. And you can go back to, I'm not sure whether Stewart had write this, but there is so many probability book online. You can just look it up yourself. Okay, I can include some video maybe on Canvas. So anyway, we can see here that independency actually tells us that they're actually independent in some way. We can separate the probabilities. When we're computing the probability between within, say, x between a and b and y between c and d, then by definition of the probability density function, you have integrating from c to d, a to b of f of xy, dx, and dy. And now, since f of xy is given by fx fy, you can separate the integral, right? You do that by fx from a to b and fy from c to d. And this is simply the probability of x being within a and b, and the probability of y being within c and d. So you can see that this is sort of like the usual discrete case. If we're rolling two dice, and those two dice are independent, which is the general case, then the probability of getting, say, 2 and 3 should be 1/6 times 1/6, right? And the multiplication is indeed reflecting the case that they're independent. Okay, so when the joint probability can be written as the product of the probability, that is where x and y are independent. Okay, so let us do some example. So we see that in the previous example on the uniform distribution within the rectangular box 0, 2, and 0, 1, if we actually do the integration, so we see that the integral of f of xy infinity to infinity respect to y gives us the density of x, right? And this guy is simply a function that takes half on the box and 0 outside. So you have half within when x is within 0 and 2, right? And after evaluating, it is simply half times the square. And can do the same thing for y. This guy is simply half on the box. So it will contribute something when y is within 0 and 1, and it is half here. Integrating over x, you simply get the indicator function from 0 to 1. So this will be 0 and 1 when y is within 1 and 0, and 0 otherwise. So we see that this guy taking product with this guy is indeed what we want, right? This multiplied this is indeed the joint density function that looks like this. So we see that in our previous example, these two guys are indeed independent. So the choice of the x coordinate and y coordinate is actually independent of each other. Their probability of being in different places can be computed via the taking product like this. And this is not always the case. In most cases, they are correlated. So let us do another example on uniform distribution. In this case, let us do it on disk. So let us uniformly distribute x and y, the point on the disk. In this case, the area of the disk is 1/pi, right? Because 1 times 1 times pi is pi, 1/pi. And we have the indicator function that tells us that this guy's 1 whenever you're within the circle, and it is 0 when you're outside the circle. Okay, so now let us compute the marginal to see x and y are indeed dependent. So we want to integrate this guy over y from -infinity towards infinity. And we see that, however, these two guys, unlike the previous case, is no longer a constant. That is because when x is given, then y has a fixed rate, right? if x is, say, half, then y cannot be, say, 1, because half square plus 1 square is not 1. It's not less than 1. So the lowest possibility of y given x is actually square root of 1 minus x squared, taking minus, and the highest possibility is plus square root of 1 minus x squared. So this is the sort of a case where this is different from the previous rectangular case. And we're integrating 1 over pi, where the value only makes sense when x is within minus 1 and 1. So doing simple integration, this is a constant, so there's actually nothing to do. It will be 2 times square root of 1 minus x squared divided by pi, 1, x, when x is within minus 1 and 1. And you can do a similar argument for y and see that they have the sort of the same density. However, you see that the product of these two guys will never be the joint density function, right? And therefore, x and y are by definition not independent. And this is actually very intuitive. Let us use a very simple example. So what is the possibility of this random point, x and y, uniformly distributed on the circle, on the disk, having value where x is larger than 0.9 and y is also larger than 0.9? It is not possible, right? Because in that case, x squared plus y squared will be larger than 1. And that is precisely this orange part here. It is outside the domain, right? So it's not possible for the uniform distribution of x and y on a disk to have such value. However, independently, if we compute the possibility of x being within 0.9 and 1, then we're actually calculating every point here, right? And same thing happens for y. The probability of y being within 0.9 and 1 is the area of this guy divided by the area of the whole circle. And these two guys are always possible, right? It's possible for x to be larger than 0.9 and y to be larger than 0.1. However, they cannot happen together. That is the point. So we see that these two probabilities are positive. So obviously, the product will be positive. However, the probability of this guy is 0. So obviously, x and y are correlated. For example, when y is very large, then x can only be small, right? They are restricted by this condition that they have to be within the disk. So obviously, they are dependent. Okay, now let's do some kind of the practical exercise that you guys will encounter in the future probability course or maybe in the quizzes. So in this case, I assume that xy, the random 2D random pair, has density A, which is a constant, times x, 2x, 2 minus x minus y within the box 0, 1, 0, 1. So that's a square, 0, 1, 0, 1. So first of all, I want you guys to find the constant A and determine whether x and y are independent random variables. So to find the A, we simply observe the definition for the density function. The integration of this whole guy should be 1 on the plane. So 1 will be the integration of f on the whole R2. And by plugging the definition of f, we get A here, and that this guy only contributes on 0, 1, 0, 1, and we're integrating this function, x times 2 minus x minus y. You can do it for y or x, it does not really matters because this is a simple polynomial. And doing some algebra, you can get, at the end of the day, 5 over 12 times A. Since this has to be 1, A is forced to be 12 over 5. Okay, you can figure out a constant like that. Now, secondly, how do we figure out whether they are independent? We compute their marginal distribution, right? Compute their density of x and density of y. So f sub x, which is the density of x, is simply the integration of little f from y and all the way on the real line. And you can do the algebra. I think it's actually here. So this is antiderivative. So you get this guy. And obviously x supports are only 0 and 1. You can do the same algebra for y, and you'll see that the density for y is given by 2/3 minus y over 2, and y is supported on 0. So obviously, this two guy taken product will not be this guy here, right? So they're actually correlated. So x, y are not independent. Okay, that is how you check independence. Okay, now let's do some practical example to some degree. So say there are two independent cashiers, x and y. So you have two cashier there, and you want to check out. And we already know that their checkout time can be modeled by the exponential distribution with mean 2 and 3. So those are the waiting time, right? Maybe 2 is a 2 minute and 3 is 3 minutes. So for example, you go to Trader Joe, you have many registers, and you can either go to checkout here or checkout there. And you already know that the mean time checking out here is 2 minutes. The mean time checking out this cashier is 3 minutes. Then what is the probability of one being higher than another? So in this case, I want to ask you that what is the probability that a customer have to wait longer at the register X, which has waiting time mean 2? So that is sort of play this out intuitively. Since the cashier X has a average waiting time smaller than the cashier Y, right? So the probability of that cashier having longer waiting time than Y should be less than half, right? Sorry, should be higher than half because it is more possible to wait shortly on the cashier X, and it is more possible to wait longer at the cashier Y, right? So whatever we get for the answer, it should be larger than half, which the computation should match our intuition. Let us try to compute. So since they're independent, the density is simply the multiplication of two marginal density. And we know from the previous example that the exponential distribution with mean 2 has the formula like this. And also, obviously, you have to make x be positive. And the distribution for the density for y, which has mean 3 as an exponential distribution, is 1 over 3 e to the minus 1/3 y. So now what is the probability we want to find? We want to find a probability of x larger than y, right? The waiting time of the register which has the smaller mean is larger than the waiting time for a register having a larger mean. So that is simply this guy. This is the density. And we want to evaluate the area here, which is from x to y. X larger than or equal to y. And that is here, right? And again, you can do it both ways. Either you fix the variable x to be a constant bound, 0 to infinity. In that case, y will be within 0 and x from here to here. Or you can fix 0 to 0 to infinity in y. Then for each fixed y, x will be starting from y towards infinity. Both works. So I encourage you to try the way that I did apply. So in this case, I try y first. So y will be within 0 to x, where x will be within 0 to infinity, right? Because y is supposed to be less than x. And then it's simple algebra. So do the integration, which in this case is quite simple. And you get eventually, blah, 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 that the final formula should be 2 over 5. And again, I say that this is kind of intuitive, right? Because this is less than half, meaning that it is not really possible for the register X to have longer waiting time than Y, because X has smaller waiting time mean, right? So it is more possible for the register X to have shorter waiting time, making, as I mentioned here, that the waiting time for X less than Y is 3 over 5. It is more likely that you can have a shorter waiting time at X and longer waiting time at Y. So this shows that the model of this exponential distribution is kind of good in a sense that it reflects the reality. Actually reflects the intuition, I would say. Okay, lastly, let us introduce a important example. So if x and y are independent normal random variable with mean 0 and with variance 1, then I want to ask the density of this new random variable x plus 1. So I don't really have an example on the top of my mind now, but this is an important property in mathematics, showing that certain distribution has very, very nice property that if you are of the same class of distribution, then adding them up or subtracting both of them will give you the same class of distribution. So normal distribution is actually this type of class. It has a certain property that different independent normal distribution adding up is still a normal distribution with different variances and means, obviously. So let us do this example and let us see how this actually works. This will actually be, I think it'll be carried out in most probability course. I just present this here because it uses a lot of double integration, and we are studying this now. So let us investigate the probability of this random variable x plus y is less than z, where z is some number, okay? So we're integrating this region, just to be clear. X plus y less or equal to z, so this guy, right? So again, you can integrate it both ways. You can fix x to be constant bound and y to be a functional bound, or y to be constant bound and x to be a functional bound. So in this case, I fix x to be constant bound from minus infinity towards infinity, where y is also the functional bound. It goes from minus infinity towards the upper bound, z minus x. So here. And here is the density function. This is a n01 random variable, n0 random variable. And since I assume that they're independent, so you have simply a product. We go from y first and then go x. So the idea of this is that I want to rewrite this guy into minus infinity z, some function, say g, du. Because in this case, by definition, this gu will be our density function, right? We're finding the probability of x plus y being less than z, which is in fact this integral of some function. And that function should be our density function. So the whole goal of this problem is to rewrite this integration into some function integrating from minus infinity towards z. Okay, so based on that intuition, let us first replace the random variable, the variable here, u to be x plus y. Don't forget that we're first differentiating integration with respect to y. So du is dy, not dx, okay? X is a constant with respect to this integration. And now you see that by replacing u to be x plus y, we have the lower bound still minus infinity, because minus infinity plus some constant x is still minus infinity. And z minus x plus x will be z, which is what we desire. The first term is not changed, and the second term, y, is replaced by u minus x. So now that it plays out, first of all, I want to swap this integration order because as I mentioned, we want to make the integration from minus infinity towards z at the exterior of the integration because the interior will be our density function. So minus infinity towards z, and that can be done by Fubini's theorem. Fubini's theorem tells us that the order does not matter. And I collect the constants. It is 1 over 2 pi here. And in the integrand, we have the original term here. And I expand this guy by u squared minus 2ux plus x squared divided by 2. And now we integrate respect to dx first and then d. Okay. And now let us complete a square because I want to integrate this guy. So we see that if you carefully manipulate the term, you have half x squared plus half x squared, and so you have x squared. You have minus 2ux here, so minus 2x here, because the division of 2. And to complete the square here, we want to add u squared divided by 4, right? And that will become x minus u over 2 squared. You cannot take that u squared divided by 4 in advance, so we multiply something back here, plus u squared divided by 4. And this is independent of x, so we can take it out with respect to x. Okay, now this actually reduced to the thing that we are very familiar with. Let us do another layer of change of variable by v to be x minus u over 2. Don't forget, u is a constant in this integral. So we have dv to be dx. And this actually is minus v squared, where again, the upper and lower bound does not change because we're shifting minus infinity and infinity by some constant, which is still minus infinity and infinity. Okay, now the prefactor here is e to the minus u squared divided by 4, right? And this, again, we have done this a million times. This is root pi. So taking root pi divided by pi, you get 1 over root pi here. So this will be our density, right? Then as we call this again, we want to show that this probability is equal to integration of minus infinity towards z of some particular function gu. So this gu is indeed our density given by 1 over 2 root pi e to the minus u squared 4. So we see that, as I mentioned here, the density of x plus y is given by f of u being this guy, and actually can be rewritten as this format, which you can see that this is 2 pi sigma squared to sigma squared. So the mean is still 0 because there's no 0 here, and the sigma squared, the variance, is 2. We see that the random variable x plus y is actually of the distribution of normal distribution with mean 0 and variance 2, which is written down here. So we see that this is a very miraculous consequence. When x and y are normal random variable independent with mean 0 and 1, then their distribution adding up will be another normal random variable with mean 0 and variance 2. And that is not a consequence. Actually, it is a general principle that when x has its own of normal distribution with mean mu x and with variance sigma x squared, where y is of normal distribution, mean mu y, and variance sigma y squared, if they're independent, then the distribution, the density function for x plus y is actually normal distribution, where the mean is given by simply adding up mu1 and mu2, sorry, mu x and mu y. I didn't write this correctly. Mu x and mu y, where the variance is again simply adding up those two. So sigma x squared plus sigma y squared. Okay, so that is actually a very nice property about normal distribution. There's other class of function distribution that satisfy this property. Today we only discuss about 3 particular types. One is normal, one is exponential, and one is uniform. Okay. So yeah, let us go through this again. So this is a introducing of application of double integral, in particular on probability. And we have introduced the one-dimensional contingent random variable and 2D version. We also introduced the concept of mean and variance, where mean characterizes the average of the distribution, and variance characterizes the spreading from that mean of the distribution. And we introduced 3 particular type of distributions. One is normal, one which can be sampling using almost everything because it has a nice behavior where the tail on the right hand side and left hand side goes to 0 rapidly, and it is concentrated in the middle, which is the usual case in our statistic, like height, like weight, like most things in real life. And we usually use this exponential distribution to describe the waiting time of some stack, some queue, where if you have a waiting time of mean 1 over lambda, where lambda is a positive number, then you can model that waiting time using this distribution. And as I mentioned in the example where we have here, oh, not here, sorry, here, we actually see that this kind of modeling is well in the sense that it actually reflects our intuition. If you have a smaller mean of waiting time, then you should wait. What I'm saying. If you have a shorter waiting time mean, then you should wait. You should wait shorter, right? If you have a longer waiting time mean, then you should wait longer, which is intuitive. And finally, we have this example that shows that normal distribution has a nice behavior where if you add up 2 independent guys of them, then you can get a new normal distribution. And we also have this very practical example, which is likely to be on your quiz or in your future probability homework, that you can find out a constant by treating the density function to have integration 1 throughout the whole region that you're considering. And you can also determine whether they are independent by computing their marginal separately and see whether the marginal have a product to be the ordinal joint distribution, which is the case in this rectangular uniform distribution, but it's not the case in this circular uniform distribution because x and y in this case actually depends on each other. They cannot be jointly too high or too low. Okay, I think that would be all. So I wish you guys a very nice spring break, and I will see you guys in next week, I think. Okay, see you.